Firstly, I would like to thank the organizers for organizing this conference in such a difficult time, because as we all know that we are in the midst of a pandemic. And also, I would like to remember all the people who have lost their lives during this pandemic, because it's a very sad time for us. So the topic of my talk will be p-arton models for modular cusp forms, which is based on a work in collaboration with Devashish Koshal, who just spoke before me, and which you can find in this particular paper with having this archive number. Okay. So as Devashish already mentioned, we are physicists by training, and lots of the stuff that we will or I will say in this talk might not be rigorous enough for mathematicians. Okay. Okay, so the outline of the talk will be as follows. So am I audible? Hello? Hello?
I think you're back. I think you're having a little connection issues, but we can hear you and see you now.
Okay, thank you. So, so the outline of my talk will be as follows. So, firstly, I will introduce modular cusp forms and L functions associated with them. Then I will briefly talk about p-artic wavelets, which will be the primary machinery which we will choose to study these in a very different context. Next would be the main part of the talk, which is to say that we want to associate with each modular cusp form a vector dual to the Q expansion of the cusp form. Then we will study the Mellin transform, the p-artic Mellin transform of these dual vectors, which we will call the p-artons. And we will define Hecke type operators over these vectors. And finally, what we want to do is look at a simple toy model, as one should call it, of product of Dirichlet L functions, which has similar properties over which we can study this construction. Okay. Okay. So moving on to modular cusp forms. So for some definition, so modular form is from the upper half plane to the complex plane of weight k and level n associated to a Dirichlet character chi n. Modular n which is holomorphic on the upper half plane h is given by this expression, which transforms under the action of gamma, an element of the discrete subgroup of SL2Z. Okay, so this is the transformation rule of a modular form under the group gamma n. So, so if you are looking at the full modular group, we have the transformation Z goes to Z plus 1. And for that case, one can write a Fourier expansion in terms of Q, which is e to the power 2 pi I Z of the function f of Z, the modular form f of Z, which is in this form. So these ANs are the Fourier coefficients with respect to the series QNs. Okay. A cusp form has a particular restriction, which is it's modular, but it vanishes at I infinity. So when you take the imaginary part of Z to infinity, or Q tends to 0 limit in this series, then it vanishes. That means it has no 0 coefficient in this series. So next, for a particular cusp form, one can define Dirichlet series coming from it, use the coefficients an and define a series an by n to the power s, starting from 1 to infinity, similar to the zeta function just talked about, and which converges in an appropriate half of the complex plane for some s. Now, this can be obtained from the modular Cusp form by taking its Mellin transform with respect to the imaginary argument. So you just take the x to the real part of z to 0, and you take the Mellin transform with the imaginary argument. And then you get the L function apart from this factor of gamma function which appears. Okay. So an example of this is the modular discriminant function, which is a Cusp form of weight 12 delta of z, which is of this form, which is q times product over n goes to 1 to infinity, 1 minus q to the power n whole to the power 24. Okay. Okay. So the modular discriminant function has a q expansion of this form. So delta of z can be written as a power series in q with these coefficients tau of n, starting from n is equals to 1 to infinity. And these coefficients satisfy interesting properties, which are the following: that if tau n, we take the product of the two coefficients, that is equals to tau mn if m and n are co-prime. And it satisfies a three-term recurrence relation. So I will call it this relation, the three-term recurrence relation, as we will see that later on it will be more evident. The tau of p to the power m plus 1 is equals to tau p times tau of p to the power m minus p to the power 11 times tau of p to the power m minus 1. Okay. And moreover, there is a bound on the value of the coefficient. So the modulus of Tp for a prime p, so this is the prime, is less than equals to 2 times p to the power 11 by 2. So some of us might know this. So these were conjectured by Ramanujan for this modular discriminant function, with the third one being proved by Daly much later. So in general, the coefficient an of a modular form of weight k and level n corresponding to the discrete subgroup gamma n satisfies a similar relation where an times an, the coefficients of the modular form, when you take the product, that is equal to an n when m and n are co-prime. And again, this A is satisfied for a particular power of prime. When the argument is a power of prime, it satisfies the three-term recurrence relation, similar to tau, but now there's an additional factor of chi p times p to the power k minus 1. Okay. Okay. So, and generically, so the L function would be obtained by the Mellin transform, and the L function corresponding to the modular form or Cusp form would be given in this form: n is equals to 1 to infinity a, and the coefficients by n to the power s, and these will have a Euler product form of this nature. So note the quadratic form in the denominator appearing here, which is important for the case of Cusp forms. So the motivation of our work is to find a dual description of the Q expansion via p-adic wavelets. So we were in some sense playing around, and then we found there's a nice correspondence between the Q expansion and an expansion in terms of p-adic wavelets, and that is what I'm going to talk about. Which this the expansion in terms of the wavelets we will call p-artons. And associate the Euler product of the corresponding L functions of the p-artons with the Mellin transform correspondingly. One must point out that the construction that we are going to discuss here is not related in any way to the, at least to our knowledge, not related to the classical theory of automorphic forms. Okay, so we have not studied that part, but maybe in some future we can think of that. Okay, so next we want to move on to the main machinery which we will use, which are the p-adic wavelets. So these are analogs of the Haar wavelets on R constructed by Kozyrev, in which we will call Kozyrev wavelets on QP, which are given by this expression and which are orthonormal in the three numbers n, m, and j, where n belongs to integers, m belongs to a set QP mod set p, and j belongs to a set 1 to p minus 1. So this omega here is the indicator function centered around x0 in QP, and so we see that there is a phase factor multiplied by this indicator function. So the above can be obtained from a mother wavelet, just like in the real case. So there's a mother wavelet psi 00j by the action of the affine group ax plus p, just like in the real case. So just like the Haar wavelets were constructed over R, the Kozyrev wavelets can also be constructed using the affine group. These wavelets, moreover, are the eigenfunctions of the Vladimirov derivative operator, which is a pseudo-differential operator on QP. So I should have written QP here, defined as follows, where gamma p is the gamma function, and this satisfies the eigenvalue equation with these eigenvalues p to the power alpha times 1 minus n. Okay. So where alpha is a complex number on a suitable half plane, defined on a suitable half plane, and can be continued analytically. So but our interest is only on the index n related to the scaling of these wavelets. So we will choose the ket notation associated with the wavelets whenever possible, but note that the notation is reverse. So psi n01 of x we denote by the ket 1 minus n. Okay, so the notation is reversed. Okay, so one can define raising and lowering operators a plus minus p on these wavelets that changes the scaling quantum number by 1. So a plus minus acting on psi n0 of 1 is equals to psi n plus minus 1, which is equivalently written on the kets as a plus minus on the ket n is equals to n minus plus of 1. So remember that the notation is reversed. So on the ket, it's a plus would lower and a minus will raise. So anyways, we restrict ourselves to the subspace and by the set psi n0 1 of x, where n goes from 1 0 minus 1 minus 2 and so on, supported on p inverse zp. Okay, so we are only restricting on the space and by these basis functions, which defines the subspace H minus on L2 of p inverse zp. So the wavelets supported on this subset correspond to the eigenvalues 1, p, p square, and so on of the Vladimirov derivative operator. And moreover, when we restrict to the subspace, we have to demand that the wavelet psi 101 corresponding to n equals to 1 and the eigenvalue 1 is the ground state, and that must be annihilated by the raising operator a plus. Okay, so that's why we call it the ground state. So just like in the harmonic oscillator case, so this is the lowest state, and when a plus acts on it, it is the null gate. Okay. Okay, so next part we move on to our basic construction of constructing vector corresponding to the Q expansion of a modular Cusp form. Okay, so this is done by noting the prime factorization. So we use the prime factorization of a natural number to relate it to a wavelet in the tensor product space of this H minus P as follows. So corresponding to a prime, we have factorization of it in p to the power n p's, And for each NPs, we associate a vector in H inverse NP. Okay. So for each power of prime, we associate a wavelet NP here, or ket NP here. Okay. And then we take the tensor product. So here, all but a finite number of NPs are 0 because of the prime factorization. Only finite number for a given natural number. Only a finite number of NPs will be non-zero. So next, we associate with the Cusp form a vector in the tensor product space. How to do that? We look at the Q expansion of the Cusp form F, and note that the power of Q, the n, which sits in the power of Q, we look at the prime factorization of that. Okay, so corresponding to the prime factorization of n, which sits in the power of Q, we associate a vector like this. So therefore, corresponding to a modular Cusp form like this, we associate a vector in this tensor product space of this form. So each QP has an analog, this, the tensor product NP, and the coefficients are just sitting here. Okay, so but this can be simplified because we know that the coefficients ANs have multiplicative property, and moreover, we know that the lowering operator on the ground state, so A minus act to the power NP, when acted on the ground state 0, gives the state NP. Okay. So therefore, the previous expression can be factorized. So this is just a longer way of writing it. So I've expanded the previous expression, but this can be factorized and written in this form. Okay. So therefore, this becomes a much more simple expression. So again, this can be rearranged, noting that this sum in each of the pH sector, geometric sum can be done, and this gives you this factor 1 minus AP, the constants AP times A inverse plus P to the power K minus 1 times chi P A inverse square inverse acting on the ground state 0 of the pth Hilbert space. Okay. So therefore, what we are doing here, we are associating with each Cusp form a tensor product of vectors in the pth Hilbert space. So, or to say that F is the tensor product of vectors in each of the pth sector. Okay. So these are what we will call the partons. So we consider the vectors Fp, which lives in the pth Hilbert space H minus, as a pth parton, that is the part of the Cusp form F at the prime P. So the operator acting on the ground state resembles the form of the Euler factor for a prime of the L function associated with F. As remind you, look at this operator. This exactly looks like the Euler factor of the for the particular L function. Okay, so this operator exactly looks like that. Okay, so explicitly for each Fp, so each parton, we have a function Fp of xp supported on P inverse Zp. So which can be expanded in the wavelets by directly writing in terms of the wavelets. We find that Fp of xp is these coefficients times these wavelets. So in summary, what we are doing here, according to this correspondence, a Cusp form, which is a function from the upper half plane to the complex plane, is equivalent to the infinite set of functions Fp, which is a map from Qp to C, one function for each prime P. So the two are equivalent in the sense that if one is given a form F, we can get F2, F3, F5, and so on, and vice versa. So the construction can be done both ways. Okay. So next, what we want to do is to study the Mellin transform of these vectors or partons. So the p-adic Mellin transform. So consider the Mellin transform. So we have used the p-adic Mellin transform as defined in Goldfeld. So defined using the unitary character omega L, which determines the phase depending on the leading p-adic digit of x. So the p-adic Mellin transform is defined as this, where g of x is a locally constant compactly supported function on p, and s is a complex number, and L takes the values from 0 to p minus 1. Okay, so this allows us to calculate the Mellin transform of the Kozyrev wavelets psi n 0 1 of x, which is this. So we just plug in the Kozyrev wavelets here and compute the p-adic Mellin transform. We'll note that there is a power of p here sitting, which is interesting. So the p-adic Mellin transform of this wavelet will give you p to the power n to the power s minus half times this factor which sits here. Okay, so what happens is that the Mellin transform of the full vector parton, if one computes it, just yields this series a p to the power n p to the power 1 minus np times s minus half. Okay, so we get this series times this constants cpls, which is just the factor which is sitting here. Okay, this is just the factor which is sitting here. So I've just renamed it here. Okay, so as we can see that one can resum it for a suitable choice of S, we could have resummed it, and one would realize that this is nothing but the Euler factor corresponding to the Cusp form for prime P. For the L function coming from the Cusp form for the prime P. So now what we can do is we can combine the result for all the primes, that is the Mellin transform of the full wave function coming associated with the modular form is then obtained by taking the product of the Mellin transform of the individual FPs, the partons in each of the pH sector, and that basically gives you this series. But we can resum this series for a suitable choice of S, and that gives you back the L function times these additional factor, obviously. So although the infinite product appearing here in the prefactor depends on L, which is different for different primes, this is reminiscent of the Mellin transform with respect to the imaginary argument of the modular form to start with. So in some sense, we are getting the L function back here by taking the p-adic Mellin transform. Okay, so that is something which is hopeful. Okay, so but now that we have looked at the vectors, constructed the vectors, and constructed their Mellin transform, what we wanted to do was try to construct something like the Hecke operators, which would act on these vectors and give us this similar kind of algebra. So firstly, let us remind ourselves shortly what the Hecke operators are. So our goal would be to have some operational understanding of the Hecke operators on these vectors Fp, the partons. Recall that the Hecke operators Tm for m natural number are a set of commuting operators with action on an eigen-Cusp form like this. So this is an eigen-Cusp form which satisfies an eigenvalue equation. Moreover, they satisfy the algebraic identities Tm times Tn is equal to Tmn when m and n are co-prime, which are similar to the coefficients satisfied by the modular Cusp forms, and a three-term recurrence relation again. So TP times TPL is equals to T of P to the power L plus 1 plus chi P to the power K minus 1, where K is the weight, times T of P to the power L minus 1. Okay. So which is also similar to what is satisfied by the coefficients of the modular Cusp forms. Okay. So on the Q expansion, the action of dP can be written using two operators. So introduce Vn, which what it does is it gives you a new series by action on f of z, and it replaces each q to the power n in f by q to the power nf. So it basically scales z by m, and introduce another operator qm, which gives a new series by replacing q to the power n by q to the power n by m for n divisible by n. Okay, so it will delete terms obviously. So it gives you a series like this. So now, hence, a Hecke operator for a prime argument can be given in terms of up plus chi p times p to the power k minus 1 times vp. So it's a linear combination of u and v. So the action of u and v reminds us of raising and lowering operators on the wavelets. So u in particular is like a plus and v is something like a minus. So because a minus acting on this series basically takes a ket, increases the level of the ket. So n ket will go to n plus 1 ket. And a plus acting on this vector will reduce the level of n by 1. But remember that a plus acting on the ground state is annihilated. So obviously the first term is vanishing. But since the APs, AP to the power n satisfies an algebraic identity, the three-term recurrence relation, one can do some algebra and introduce a three-term recurrence relation and write the action of A plus in this form. Since the AP to the power n satisfy a three-term recurrence relation. Thus, what we can do is define a Hecke type, one must call it a Hecke type operator for a prime argument TP is equals to A plus chi p times p to the power k minus 1 A minus. Okay. So, and this action, as we can check, this action of TP on the parton S of P gives you back the eigenvalue AP times F of P. Okay. So, but the problem was to define it a bit more rigorously. So unfortunately, the self-adjointness of chi star half of P times TP is not straightforward using a suitably chosen inner product. So what we were trying to do was introduce an inner product similar to the Peterson inner product. So we wanted a weight factor of mod of x to the power k minus 2. But this operator defined here on the wavelets is not self-adjoint under that factor. So obviously this was not working. So then we realized that one can choose a more convenient set of wavelets which are orthogonal under the multiplicative invariant measure. So capital psi here are defined by mod of x to the power half. So there is an additional factor of mod x to the power half, and this is the p-adic norm of x times the traditional Kozyrev wavelets, and these are orthonormal under the multiplicatively invariant measure by the orthogonality of the Kozyrev wavelets. Moreover, what we do is we slightly modify our partons. So corresponding to this vector fp of xp, we change the expansion coefficients by a factor of p to the power minus k minus 1 by 2 np times ap np times the multiplicative variable. So now we are expanding the partons in the multiplicative the orthogonal wavelets. Okay, so next, what we do is we define an inner product of two functions with respect to the scale invariant measure, d cross of x on qp cross, like this, f and g. And moreover, we can explicitly define the raising and lowering operators, a plus acting on f and a minus acting on f, like this, which are given as an integral over the wavelets like this. So this is just like how we do in quantum mechanics, how we expand, write the raising and lowering operators in terms of the eigenkets of the number operators. It's exactly analogous. So because these are the basis functions, and we just write the raising and lowering operators in terms of the basis functions. Okay, so once we define our a plus and a minuses in this fashion, it is easy to check that the Hermitian adjoint of a plus is a minus under this inner product, and the Hermitian adjoint of a minus is a plus under this inner product. Then one can show is one can define a Hecke type operator again, TP, which when acted on the modified parton. Okay, so is there any question? Okay. So so TP, so we define a modified Hecke type operator, which when acts on the modified definition of the parton, gives you the eigenvalue equation of this form. The TP acting on FP is equals to P to the power minus K minus 1 by 2 AP of FP. Okay, where TP is defined as A plus chi P A minus. More importantly, what we obtain by defining TP in this fashion is that one can calculate the Hermitian adjoint of T, and it is indeed chi star of P times TP, okay, which is true for the Hecke operators. So this is what we had wanted to achieve, which was not possible using the previous construction. Okay, so as a consequence, we immediately obtain that if we have two eigenfunctions, f and g of the Hecke type operator TP, then immediately they are orthogonal. Okay, because AF and AG star are different. So these are different, distinct eigenfunctions. Okay, and moreover, we obtain that the chi star to the power half times AFP are real. Okay, simply because one can define a Hermitian, so one can define chi star whole to the power half times TP, which is directly self-adjoint by from this formula. Okay. Then we obtain that chi star to the power half P times AF are real. Okay, so how much time do I have? Fairly not fairly. Not much time. So now what can do is from the inner product of f and g, one can of two partons, one can deduce a perceivable type identity. So basically what we do is we have the inner product of F and G, and we deduce a perceivable identity via the Mellin transform. So we introduce the Mellin and its inverse here, and we deduce the perceivable identity. So therefore, the inner product of F and G can also be written in the Mellin space as an integral over LF of k minus 1 by 2 plus IT and LG of k minus 1 by 2 plus IT, where these are nothing but the L functions, the local L functions corresponding to the Cusp form. Okay, so this is the Euler factor sitting here. It's just the Euler factor which is sitting here due to the Cusp form. Okay, so what one can obviously evaluate this or the inner product of F and G directly from the wavelet expansion, and both of them give you the same result, which is this is a sum over NP, p to the power minus k minus 1 NP, and there's a product of the coefficients of AF p to the power NP and AG p to the power NP. So it might be surprising that why this sum is 0. When we had obtained this, we were also thinking that why would this sum be 0? But as it turns out, one can show that this sum is actually 0. So how to realize that? So looking at the quadratic in the denominator of the local L function LP f of f, which has two roots, a1 and a2, given by p to the power k minus 1 by 2 e to the power I alpha 1 and p to the power k minus 1 by 2 e to the power minus I alpha 2. So this is like sign which is chosen. Then a. So is there any question? Okay, maybe not. So AP are the sum of the roots A1 and A2, as one can see in the Euler factor. So that is given by 2 cos alpha 1 plus alpha 2 by 2 times p to the power k minus 1 by 2 times p to the power alpha 1 minus alpha 2 by 2. And chi p is e to the power I alpha 1 minus alpha 2. Okay, so as it turns out, this is indeed consistent with the condition of the growth of the coefficients. As if we take the modulus of AP, this is obviously less than 2 of p to the power k minus 1 by 2. As you remember, for tau of p, the modular discriminating function, it was 2 to the power p to the power, this mod of tau p was less than 2 p to the power 11 by 2. Okay, so why is this important? The function LPS of f, which is the local factor, local Euler factor of the L function, is nothing but the generating function of the orthogonal Chebyshev polynomial of type 2. So denoted by un of x. Okay. So here I've just written the generating function of the Chebyshev polynomial of type 2. So this is 1 minus 2 t cos theta plus t square, where theta is half of alpha 1 plus alpha 2, and t is this argument. So if you just plug it in here, this is nothing but the local Euler factor LPS of f. And one can do a series expansion of this, and this will give you the orthogonal Chebyshev polynomial of type 2 un cos theta. Okay. Now, importantly, this un satisfy the 3-term recurrence relation, which is exactly similar to the 3-term recurrence relation satisfied by the coefficients a's or the operators TPs, Hecke algebra, Hecke operators, apart from the factor of factor of p to the power k minus 1 times chi p, which can be somehow reabsorbed in the algebra and then shown to be identical to this three-term recurrent solution. That's why I had stated that those are three-term recurrent solutions. Okay, so u0 of zeta with argument zeta is 1, and u1 of zeta is 2 cos zeta. Okay. So then the orthogonality of the partons f and g are corresponding L functions, which we had obtained in this integral. So I will go back here. So this integral here, which one would evaluate and get this, the orthogonality is nothing but a consequence of the expression of identity via the Chebyshev polynomial of polynomials of type 2. Okay, so there is a weight factor coming here. So I have dropped that weight factor. So this explicitly proves the orthogonality of the partons which were constructed and their Meli dual, which are eigenfunctions of the Hecke operators defined. Later on, so when we realized this, we did not know whether people had realized this earlier or not. Later on, we realized that the appearance of Chebyshev polynomial of type 2 in similar context in the study of the distribution of the eigenvalues of Hecke operators had been studied by Condrey et al. And Serre. So next, what we intend to study is a class of functions for which these properties are manifest by construction. So in some sense, we want to construct a toy model where we want to see this algebra from the very beginning. To do that, what we want is we would take the product of Dirichlet L functions. Okay, so I think I have about 20 minutes. Yeah. So what to do is we look at a similar case of a Dirichlet L function corresponding to a Dirichlet character nu. We know that the Dirichlet L function can be written in this form, where nu of n is a Dirichlet unit character, which exhibits a Euler product of this fashion. But our goal is to mimic the properties of modular L function, and how to do it, we would take product of two Dirichlet L functions with the complex conjugate characters. So we define 2Ls nu as product of Dirichlet L functions with complex conjugate characters. Okay, and as a consequence, what you obtain here is an Euler product of this form. And once we do a series expansion on the left and combine these factors in the Euler product, we immediately obtain a similarity to the modular L function. So this is like k equals to 1 case and chi p is equals to 1 case in the in analog to the modular L function. Okay. But the advantage here is that you can see the denominator is already in the form of the generating function of the Chebyshev polynomials. Okay. As I said, that u star is the complex conjugate of the character nu. Okay, so so a local factor 2LP, as I mentioned, 2LP S of nu at a prime P can be recognized as the generating function of the Chebyshev polynomial of type 2, and one can immediately obtain the series expansion with these coefficients appearing here. So then the N's are basically the products of these N's are just the products of these Chebyshev polynomials. Okay. And A for a power p to the power np is unp appearing here. So remember that the Dirichlet L function is related to a theta series of this form, where nu is a primitive Dirichlet character modulo capital N, and epsilons take the value 0 or 1 depending on whether nu is even or odd respectively. So the Mellin transform of this with respect to the imaginary argument Iy of the theta series gives us back the L functions, similar to what we had seen in the case of the modular transforms. But now 2ls nu can be written as this using the Mellin transform of the individual L functions. And we realize that 2ls nu is the Mellin transform of the convolution of two theta series. Moreover, one can explicitly expand once one plugs in the series form of the theta series here. We obtain these a series of this form where we have these basis functions appearing. Okay, so this is important as we will see later on in a moment. So we know that the theta series has the following transformation property, that if we take the imaginary argument, if we inverse the imaginary argument, y goes to 1 by y, then there is a transformation relation like this. Okay, where tau of q is the Gaussian, but this is unimportant for our present case. We want to calculate the transformation relation of the convolution of the two theta series, and as it turns out, the convolution of the theta series transforms by a factor of 5 to the power 1 plus 2 epsilon. Okay. So this is interesting to note because this property, as the explicit expression on the RHS of 53, which is this form, as I said, with the modified basis functions, are reminiscent of the harmonic mass-like waveforms, okay, but restricted to purely imaginary arguments of weight 0. So that's why we call it mass-likes, because the relation is only for y goes to 1 by y. So there is a tilde here. Okay, so we can associate a series like this, and we can check that this series will satisfy the hyperbolic Laplacian on the upper half plane. So nevertheless, the y goes to 1 by y transformation of this series, so for x equals to 0, is similar to what appears in Koshlyakov identities, with similar series with basis modified basis function k0, which appears from taking the squares of the simplest one appears from taking the squares of Riemann zeta function, and there these coefficients are divisor functions. Okay, so this came as a pleasant surprise to us. And anyways, from now on, we will put new to be even. So the motivation to do all this was to construct a Partonic model for such a function. So that we can do here by choosing the pth factor f p nu of x as this. So here the coefficients a p to the power np's are directly the Chebyshev polynomial of type 2s, and this is expanded in terms of the multiplicatively orthogonal wavelets. And as a consequence, one can directly check the orthogonality of the partons here. We can, because of the orthogonality relation of the Chebyshev polynomial of type 2. And this also tells us that if one takes the inner product of their tensor products, they are also orthogonal. Okay, so that gives us a relation of this form. So, which is when we take these coefficients AF and AG. So minded these are real, so there is no meaning in taking the complex conjugate. But anyways, when we take these coefficients AF and AG coming from two products of L functions, corresponding to two different Dirichlet characters, modulo n, capital N, then when we take the sum, that sum must vanish in a loose sense. Okay, so because they are orthogonal. Simply because these coefficients are orthogonal functions, now directly related to orthogonal functions, the Chebyshev polynomials of type 2. Okay, so an analogous inner product exists on the space of mass-like waveforms, which we had defined. So, so we choose a rectangular domain in the upper half plane, and one can check that if we choose this inner product in that rectangular domain, we would get orthogonality relation, which yields the same sum over the coefficients f and ag. So now the last point that I would make is the above inner product can be related to the inner product of corresponding full L functions in a bit non-rigorous way. Because we have a series of this form, so one can replace in delta mn the Kronecker delta, the Dirac delta, and then do a formal manipulation, and then choose analytic continuation of the individual series to write an integral of this form. So then the inner product of the full parton, full vector corresponding to the product of the partons would boil down to an integral over the L functions of this form. Okay, so this was interesting to us. The final expression, or although so sorry, there's a typo, so there are two although. So although obtained by some formal manipulation, is perceivable type identity interpreted as an inner product over 2LF and 2LG. So this somehow indicates that the L functions seem to be orthogonal, but we have not verified this numerically in any way possible, because as you can see, it's on the critical line and the L functions are wildly oscillatory there. So to summarize, or to talk about the outlook, which we would like to pursue later on, is we leave the study of the action of the group GL to QP on these partons to future study. This might have connection to the classical theory of automorphic forms, we don't know, but it would be interesting to see. Moreover, the construction is also suggestive of a holographic correspondence, where the data of a function f in the upper half of the complex plane is related to tensor product of QP, which in turn is related to the real line, which is the boundary of the upper half plane. So, moreover, so there's a possible interpretation of 2L, so the product of the two Dirichlet L functions, as the Mellin dual of the partons, and hence we would very much like to see whether one can construct Hecke-like operators on them and make the statement of orthogonality more rigorous. As of now, we have not been able to do that, but we hope to answer these questions in the future. Okay, so thank you for your time and listening to me. So any questions?
Yes, thank you for an excellent talk. Any questions out there from the audience? Looking here, I see no immediate questions. Right here, though, I as a number theorist, I will ask a question, and maybe the answer will be the same as before. But to what extent is it possible to kind of move some of the things that you're studying for kind of classic L functions or L functions over Q to other number fields?
We have not thought about it honestly.
That's fair. I'm a number theorist, so that's kind of the natural first question. But as a physicist, that might be less important.
Yeah. So actually, basic thing that we observed was this, which was also said, that this Euler product for when you have a quantity in the denominator, this is related to the Chebyshev polynomials, generating function of Chebyshev polynomials of type 2. So, and that when we had obtained this orthogonality relation, we did not know whether this is true or not, but later on we realized that it made sense once we related to this Chebyshev polynomials. To other cases, obviously, I'm not sure whether those cases have the same pattern which appear here. So we kind of need this quadratic form in the denominator. But I'm not sure whether that is possible in other cases. So we have to look. Probably that's the answer.
Yeah, no, that makes sense.
Could I make a comment, please?
Of course.
Yes, yes.
Yeah, actually, one of the tools that we use is this set of orthogonal eigenfunctions, orthogonal basis, which are eigenfunctions of this pseudo-differential operator, which are these Kozyrev wavelets. So, I mean, physicists naturally tend to use analytical methods, as you may know. So that is, we had this, and that was a useful tool. So we haven't really thought about more general cases, and if there is some analog of this kind of vector space available in those cases, then it should not be, in principle, it should not be too difficult to try to see how this can be generalized. So that's what I can think of offhand. But
No,
it's the reason that we didn't think was that it was the availability of the tools here was something that helped us.
Yeah.
Very, very sensible. Yeah, to start with something with the orthogonality and understand the result. Fascinating. Other questions or comments from people in the audience? All right. Well, if not, let's thank the speaker again.
Okay. Thank you.
Very interesting. Thank you. So we will
sharing.
Yes. I can make that happen here in a second. So we have about 3 minutes if people want to wander and get coffee or something and come back. But we will return in just a couple minutes here with our final talk of the morning session.
Chris, I suggest you stop the recording so it will be easier for Wilson to separate the talks.
Okay, but you have to promise to remind me to start the next one or else.
Yes, okay.
Okay, thank you.